So we've spent the last couple of sessions really laying the groundwork, talking about length and time, those fundamental engineering dimensions.
Right, the ones defining space and duration.
Exactly. And today we tackle the third big pillar, the one that governs, material quantity and resistance.
Mass. That's our focus. Mass and all the parameters related to it.
So what's the mission for this deep dive then?
Okay, our mission is to get past just thinking of mass as, like, heaviness. We need to really grasp it as the quantitative measure of matter itself, and maybe more importantly for engineers, as the key measure of resistance to motion, to dynamic change.
Ah, okay. Resistance to change. That's crucial.
It really is. If you're designing anything that moves or bears a load, a bridge, a car, a rocket, understanding mass properly, not just weight, is absolutely critical.
Okay, sounds good. So let's outline the plan. How are we going to unpack this?
We'll start small, right? Go microscopic. Look at the building blocks.
Atoms and molecules.
Exactly. Then we'll scale up to static properties, how we measure mass, density, that kind of thing.
And then the dynamic stuff, mass in motion.
Yep. Momentum, rotation, inertia.
Yeah.
And we absolutely have to cover the golden rule, conservation of mass bookkeeping.
Excellent. Let's dive in, starting at the absolute fundamental level.
Right.
So everything around us, different forms, different shapes, but it all starts with atoms, yeah.
Pretty much. Those 106-ish known chemical elements on the periodic table, and they're made of even smaller bits.
Electrons, protons, neutrons, the classic trio.
That's them. And mass, fundamentally, gives us a way to quantify how many of these atoms or molecules are packed into an object.
So it's like a count, a measure of the amount of stuff.
Precisely. A quantitative measure.
Yeah.
Think about water. A single H2O molecule is the smallest bit that still behaves like water.
Okay.
A glass of water just has billions and billions of them. Its mass is the sum total of all those tiny molecules.
Right. And water is a great example for states of matter, too.
Yeah.
Ice, liquid, steam.
Absolutely. You cool water below 0 Celsius. At standard pressure, you get solid ice.
Heat it between 0 and 100, it's liquid.
And above 100 degrees C, it turns into steam, a gas.
It seems so different, though. Solid, liquid, gas.
Visually, yes.
Yeah.
Dramatically different properties. But here's the amazing part, and you can take this even further.
How so?
If you superheat that steam, say, above 2,000 degrees Celsius, the molecules themselves break apart.
Into what?
Into plasma. Basically, a soup of free electrons and nuclei.
Whoa. Okay.
But here's the absolute key takeaway for you listening. Ice, water, steam, even plasma. The phase changes dramatically, but the total number of atoms and molecules, the underlying mass, stays exactly the same. It's constant.
Okay. The amount of stuff doesn't change, just how it's arranged.
Precisely. And that constancy is why mass is a fundamental dimension in engineering. It's reliable.
And it's that constant value that really separates mass from what we often, mix it up with.
Wait, that confusion is huge and historically kind of understandable.
How come?
Well, before we really understood gravity properly, people mostly just experienced how hard it was to lift something. That felt like the defining property.
Which is weight.
Which is weight, yes. The force exerted on the mass because of Earth's gravitational pull. Mass is intrinsic, it's the stuff. Weight is the interaction of that stuff with gravity.
So if I took a kilogram of apples to the moon...
That kilogram of apples still has a mass of 1 kilogram. That hasn't changed.
But it would weigh less, right? Because the moon's gravity is weaker. About 1/6, I think.
Exactly right. Your kilogram of apples would feel much lighter, easier to lift. Its weight would be about 1/6 of its Earth weight.
And engineers have to account for that. Designing a lunar lander based on Earth weight would be bad.
Catastrophic, probably.
Yeah.
The landing gear would be way too heavy, massively over-engineered for the moon's gravity. You design based on mass, then calculate the local weight force wherever you are. Earth, Moon, Mars, wherever.
Okay, let's nail down the units then, because this is where engineers need to be meticulous. It gets confusing with different systems.
It really does. The standard international unit, the SI unit, is the kilogram. The kg, that's the one we try to stick to.
But in the U.S., we still often use pounds, right?
Yes, the U.S. customary system uses the pound mass, or LEBM. And just to complicate things, there's an older British system, the British gravitational system.
Oh, yeah, I've heard of this, the slug.
The slug. It's a fascinating one because it's defined differently. In that system, you define the unit of force, first the pound force, pound BF, and acceleration. The mass unit, the slug, is whatever makes Newton's second law work out nicely with those units.
Okay, that sounds potentially confusing.
It can be,
Yeah.
especially for international projects. 1 kilogram is about 2.205 pound mass, for reference. But sticking to kilograms, the SI standard, really helps avoid errors.
Makes sense. Now, if mass is this intrinsic thing, how do we actually measure it? When I step on my bathroom scale, it gives me a number instantly. It feels like it's measuring mass.
But it's clever.
Yeah.
We measure it indirectly. That scale isn't counting your atoms. It's measuring the downward force you exert on it, your gait. Inside the scale, there's usually a force transducer.
Like a spring or something more modern.
Could be a spring in older scales, yeah. More often now, it uses something called strain gauges. Tiny electronic components that change their resistance when they're deformed.
So my weight squashes them a bit.
Exactly. It causes a tiny deformation, a strain. The scale measures that electrical change, relates it to the force your weight, and then it calculates what your mass must be, using the known value of Earth's gravity.
So it's doing a quick calculation. Okay, gravity here is 9.8 meters per second squared. The force is x, so the mass must be x divided by 9.8, something like that.
That's the principle, yes. It's an inference based on the local gravitational force. It assumes you're on Earth.
Which is why my scale would read wrong on the moon.
Precisely. It's calibrated for Earth's gravity.
Okay, got it. So we've covered fundamental mass, measuring it. Let's move to those derived properties, quantifying how compact matter is.
Right. You mentioned having a cubic foot of wood versus a cubic foot of steel.
Yeah, clearly the steel has way more mass in the same amount of space. How do we quantify that compactness?
That brings us to a super important tool, density. Usually represented by the Greek letter rho,
Free dollars?
and density is simply the ratio of an object's mass to the volume it takes up. So the horo equals mass divided by volume. It tells you how tightly packed the material is.
So high density means lots of mass crammed into a small space, like gold or lead.
Exactly. Or mercury, very dense materials. Wood, on the other hand, is much less dense, lots of air pockets in its structure.
And density isn't always fixed for a material, is it? Temperature matters. Pressure?
Absolutely critical point. Density changes sometimes significantly with temperature and pressure. Think about air heated up, it expands, density goes down. Cool it, it contracts, density goes up.
Water is the famous weird one, right? When it freezes.
The classic example, water expands when it freezes into ice. Same mass, but it takes up more volume.
So its density decreases.
Which is precisely why ice floats on liquid water. Its lower density makes it buoyant. A crucial property for life on Earth, actually.
Wow, yeah. Didn't think of it that way. You mentioned the inverse of density, too.
Yes, specific volume. That's volume divided by mass. It gets used a lot in thermodynamics, especially with gases, where volume changes are really important.
Okay. But for comparing different materials, solids and liquids, there's another useful one.
Specific gravity, often abbreviated as SG. This is a really neat unitless measure.
Unitless. How does that work?
It's a ratio.
Mm-hmm.
Specific gravity is the density of your material divided by the density of a reference substance. And for liquids and solids, that reference is usually water at a specific temperature, typically 4 degrees Celsius, where water is most dense.
So it's comparing everything to water.
Exactly. It gives you a quick sense of how dense something is relative to water.
So looking at the table from our source material, mercury has an SG of 13.55.
Meaning it's 13.5 times denser than water. Heavy stuff.
Cast iron is about 7.2, still much denser than water.
Mm-hmm.
But then mahogany wood is 0.55.
And that number instantly tells you something important.
It's less than 1, so it's less dense than water.
Which means,
It floats.
bingo, anything with an SG less than 1 will float in water. Anything greater than 1 will sink. It's a very practical number.
Makes sense. Should we quickly mention specific weight?
Good point. Specific weight is related. It's the weight per unit volume rather than mass per unit volume. So it's just density multiplied by the acceleration due to gravity, or G. It pops up in fluid mechanics calculations sometimes.
Okay, let's shift gears now. Away from static properties and into dynamics, mass and motion.
Right, and this is where mass really shows its character, as that resistance to change in motion you mentioned earlier.
My example,
Yeah.
pushing a small car versus a huge truck, same effort from me.
And the truck barely moves, right. It resists your push much more effectively because it has much more mass.
How do we quantify that resistance in motion?
With momentum. Symbol usually Neveler or sometimes Ben-Hours. Momentum is simply the product of an object's mass and its velocity. So $1 m times v dol.
Mass times velocity. Okay.
Think about football. 2 players running at the exact same speed. One's a big linebacker, one's a smaller running back.
The linebacker is harder to tackle.
Much harder. Because even at the same velocity, their greater mass gives them significantly more momentum, more oomph to keep going.
And this ties into that surprising fact about momentum, right? Something small can have huge momentum.
Absolutely. Like a bullet. Very small mass, obviously.
Say.
But fired from a gun, it has an incredibly high velocity. That high velocity means even with a small mass, it has enormous momentum.
Which is why it's so dangerous.
Yes.
Okay. And what about the stunt performer example? Falling from a height.
Great illustration. As they fall, gravity accelerates them, so their velocity increases, and their momentum builds up massively just before impact.
How do they survive that huge momentum hitting the ground?
They don't hit hard ground, they hit something soft, like a large airbag or a pile of cardboard boxes,
To cushion the blow.
to increase the time over which that momentum changes to zero. This leads to impulse force multiplied by the time it acts. Impulse equals the change in momentum.
Ah, so if you increase the time of impact.
By landing on something soft that compresses over, say, half a second, instead of hitting concrete in a millisecond.
The force required to stop you is much, much lower.
Exactly. Spread the change in momentum over a longer time, and the peak force drops dramatically, hopefully to survivable levels.
Yeah.
It's fundamental physics applied to safety.
Clever. And you mentioned the common misuse of momentum, the aha moment.
Oh, yeah, this is a pet peeve for physicists listening to sports commentary.
What happens?
Well, momentum is mass times velocity. And velocity is a vector. It has magnitude and direction. If something isn't moving relative to you, its velocity is zero.
Okay.
So if an object or a person or a whole team sitting on the bench during a timeout is at rest relative to the Earth,
Their velocity is zero.
which means their momentum is.
Zero. Mass times zero is zero.
Exactly. So when the commentator says, well, they really gained some momentum during that timeout, while everyone's just sitting there, technically that's incorrect. Their momentum is zero. They might have gained psychological momentum, but not physical momentum.
Huh. Good point. Okay. Physics versus sports talk. Got it. Let's pivot from moving in a straight line, linear motion, to spinning, rotation.
Right. Because how mass is distributed becomes incredibly important when you're talking about rotation.
It's not just the total mass, but where it is.
Precisely. And we quantify the resistance to rotational motion using a concept called mass moment of inertia, often symbol any dollars.
Okay, mass moment of inertia, what does that tell us?
It measures how hard it is to start something spinning or to stop it once it's spinning. Think about maybe an ice skater.
Okay, pulling their arms in to spin faster.
Exactly. When their arms are outstretched, the mass of their arms is far from the axis of rotation, their body's center line. This gives them a large moment of inertia. It's harder to spin up.
But when they pull their arms in close?
They bring that mass closer to the axis of rotation. This decreases their moment of inertia significantly. And because angular momentum tends to be conserved, their rotational speed has to increase to compensate. They spin much faster.
So the farther the mass is from the center of rotation, the harder it is to rotate.
That's the key takeaway. Mathematically, for a simple point mass dollars at a distance $20 from the axis, the moment of inertia is the dollar times $20 2 lambust.
Why is the distance squared? That seems important.
It's hugely important. That $20 2 term means that mass located far from the axis contributes much more to the moment of inertia than mass close to the axis. Doubling the distance quadruples its contribution to inertia.
Wow. Okay, so engineers designing, say, a flywheel or a turbine blade.
They have to be acutely aware of this. Moving even a small amount of mass further out from the center of rotation dramatically increases the energy needed to spin it up or slow it down. It's a nonlinear effect.
And for more complex shapes, like a solid cylinder.
We use calculus integration to sum up the $20 contributions of all the little bits of mass. But there are standard formulas for common shapes. For a solid cylinder rotating about its central axis, its $$ is 12 meter R22, where R is the outer radius.
Okay. Inertia. Got it. So final big topic, mass accounting, bookkeeping.
Yes. Engineers, at heart, are very careful bookkeepers. We have to track mass, we have to track energy, we have to track momentum.
And the fundamental rule for mass bookkeeping.
Conservation of mass. You can't create it, you can't destroy it within the bounds of normal engineering problems. What goes in must come out, or it must pile up somewhere.
Okay. Not created or destroyed. How do we apply that?
We often think about it using a control volume. This is just a specific region in space that we as engineers define for our analysis. It could be a pipe section, a pump casing, a jet engine, even this room.
So we draw an imaginary boundary around what we care about.
Exactly. And then we apply the conservation principle to that volume.
Yeah.
The simplest way to think about it is the bathtub analogy.
Okay, I like analogies. The bathtub is my control volume.
Your bathtub is the control volume. Water flowing from the tap is mass coming in. Water going down the drain is mass going out.
Okay.
If the tap flow rate equals the drain flow rate, rate in equals rate out. What happens to the water level in the tub?
It stays the same, steady state.
Right. Mass in equals mass out, so there's no change in the amount of mass stored inside the control volume.
But if I plug the drain,
Now rate out is 0, but rate in is still happening. Mass is flowing in, but none is leaving.
so the water level rises, the amount of mass inside my control volume increases.
Exactly. You get accumulation. Mass in minus mass out equals the rate of accumulation or depletion if rate out is bigger than rate in
Yeah,
inside the control volume. That's the formal state.
that makes perfect sense. It applies everywhere.
Chemical reactors, rivers, air flowing into lungs, fuel into an engine.
Hmm.
It's universal.
And you mentioned the queuing analogy, like waiting in line.
Yeah, that's a perfect everyday example of mass conservation if you think of people as the mass.
How so? The queue is the control volume.
The queue is the control volume. People arriving join the line that's rate in. People getting served and leaving the line that's rate out.
And when the line gets really long, like at the supermarket checkout during peak hours.
That means the rate in, customers arriving, is temporarily greater than the rate out, customers being served.
Mm.
So you get accumulation. The queue length increases. It's a mass balance problem.
Yeah, never thought of it that way. Okay. And to quantify that flow, we use
Mass flow rate, usually symbol dm live dot on thing. It's simply the amount of mass flowing past a point or across a boundary per unit of time. So mass divided by time. Kilograms per second, for instance.
why mass flow rate? Why not just volume flow rate, like gallons per minute?
Because for many processes, especially involving gases or reactions like combustion, the mass is what matters. Volume can change drastically with temperature and pressure, but the mass flow tells you how much actual stuff is moving through.
Okay. So the Dano gives us the real quantity.
Exactly. And it's directly related to volume flow rate, of course. Mass flow rate equals density times the volume flow rate, often symbol Q or MoQ.
Right. And we saw this in the source materials calculation for a car burning gasoline.
Yes, example 9.4. They needed to figure out the mass flow rate of fuel required. They knew the car used gasoline with a specific gravity, SG, of 0.72.
Which lets you find the density.
Right, SG times density of water gives you gasoline density. And they knew the car consumed fuel at a certain volume rate, related to 15 kilometers per liter.
So density times volume flow rate.
Gives you the mass flow rate. The calculations showed it needed about $4.322 kilograms of gasoline per hour to run at that condition. That's a critical number for designing the fuel pump, the injectors, everything.
Links, density, volume, time, all together.
Okay. So let's try and summarize the key things for you, the listener. Mass is foundational. It's not weight. You've got to keep that distinction clear.
Intrinsic property versus gravitational force. Got it.
Then you have the derived properties. Density and specific gravity tell you about compactness, how much mass is in a given space. Static properties,
Right.
and then the dynamic ones. Momentum tells you about mass in linear motion. It's a resistance to stopping or starting. Mass moment of inertia tells you about resistance to rotational motion.
And finally, conservation. Mass in equals mass out plus accumulation, the bookkeeper's rule.
Those are the essential tools engineers use constantly when dealing with mass.
Okay, great summary. Now, for our final thought, let's loop back to mass as a static property, but connect it to something else vital: energy. Specifically, thermal energy storage.
Ah, good one.
Yeah.
Yes, mass plays a huge role there, too. A material's ability to store heat isn't just about its specific heat capacity. It's also about how much of it there is. Total mass matters.
This is the idea behind passive solar houses, right? Using massive elements.
Exactly. You see designs with thick concrete floors, heavy brick walls, sometimes even large barrels of water placed strategically.
Why those materials high mass?
High mass, and often decent specific heat capacity. The idea is that during the day, sunlight streams in and heats up these massive objects. They absorb a lot of thermal energy because there's simply a lot of material there to heat up.
They soak up the heat like a sponge?
A thermal sponge, yes.
Mm.
And because they have so much mass, their temperature doesn't rise super quickly, but they store a large amount of energy. Then, overnight, as the air cools down.
The massive floor or wall slowly releases that stored heat back into the room.
Precisely. It helps keep the temperature stable without needing as much active heating. Water is particularly good for this because it has a very high specific heat capacity and it's dense. A barrel of water can store much more heat than the same volume of air.
So mass acts as a thermal battery, in a way.
A passive thermal battery,
I
exactly.
Okay, so here's the final thought for you to ponder, building on all this. Knowing that mass is key for stability, for resisting motion, and for storing thermal energy. If you were designing a building specifically to maintain a very steady internal temperature using only passive solar energy, what material property related to mass would you prioritize most? Would it be its raw density, its specific heat capacity per unit mass, or maybe something related to its structural inertia? Think about what delivers the best thermal stability. That's your takeaway for this deep dive.